Hi, my name is Casey Joyce, and this lab was the Create Your Own Adventure Lab. I chose to film a video of me kicking a basketball against a wall to show an inelastic collision. I also wanted to measure if the energy and momentum principle was true and that the energy was conserved. The energy principle states that the change in energy is equal to the work or equal to the change in kinetic energy. In this case, I found that the change in energy was equal to 0. This is because the net force was equal to 0 and the velocity was constant. You know the net force is equal to 0 by using Newton's second law to predict the position. Newton's second law states that V final equals V initial plus F net divided by the mass times the change in time. We were able to use that and put it in a loop in the code to predict the position and therefore predict the change in energy. I found that there was a constant velocity and net force of 0. Also, the momentum principle states that the momentum final was equal to momentum initial, and I'll show you why. Here's the video that I filmed on Tracker. I set the origin equal to the ball, and the inelastic collision is right there as it hits the wall and then comes back. Here is my code. Some of the things that were interesting to point out were the different while loops. You first had to do a while loop before it was 0.5 seconds. This is, at 0.5 seconds, is when it hit its peak, is when the ball hit the wall and the collision happened. Because it's going up in the positive x direction and then it's going back in the negative x direction, you had to do two different while loops, even though the concepts were the same. There was the force of gravity, which is the negative mass of the ball times g times the unit vector, which was also canceled out by the normal, the force of the normal, to get you an F net of 0. You can see some of my givens over here. You had to create average velocity. To do that, I took the point at the peak right here, which was 2.69 meters, minus the point at when it first started, and then the time, which I got the average velocity to be 2.66 meters per second. The net force was equal to the force of gravity plus the normal force, which was equal to 0 because they both canceled each other out. Some other interesting things to point out were what is the force that the wall exerts onto the ball, and how does it impact the velocity? When the ball hits the wall, there is a time between, you first have to figure out the time between the contact with the ball and the contact with the wall and when the ball comes to a stop. To do that, I looked at these 2 points right here. It hits the wall at 2.639 meters. Around it is 2.639 and 2.518, and it's 0.3 seconds in between all these things. So by finding the average of that, you found that it's 0.167 seconds of time elapses when the ball hits the wall and it comes to a stop. This you could then use to calculate the force of the wall, which is equal to the ball's mass times the acceleration. Acceleration was calculated by doing the velocity divided by the time between the contact with the wall and the ball, which equaled 18,158.08 newtons. This is a lot bigger number, especially when you compare it to the force of the gravity, which is just ball times the gravity constant, which is 5,586 newtons. To find net force, you also calculate in the normal force, which would be negative 5,586 newtons. Another thing to consider is how the momentum stays constant. When you run my code, which I'll show you in one right here, we looked at just the horizontal concepts because that's how you can see the momentum is constant. The ball goes to the right at a constant velocity, and then as it hits the wall, which marks at around right there, 0.5 seconds, it goes in the other direction, shown by this graph and this plot right there. I then had the code print the momentum. This is the position right here. It ended at negative 2.66 because that would be the peak, which is at 2.66. And the momentum was 3,032. In both on the way there and on the way back, the momentum stays constant because the velocity is constant. So the question is, why is that? Why does the momentum stay constant? Why is momentum conserved during the collision? Is it conserved during the entire experiment? Well, there is constant momentum during the actual collision, but it's only during the collision. When you're looking at a collision, especially inelastic collisions, you need to look at right before the ball hits the wall and then when it hits. You don't need to look at any other thing leading up to that. When you're looking at just that, the ball's going to hit the wall so spontaneously that gravity has no time to change. So therefore, the momentum is constant, as is the energy is conserved, because work is equal to 0. But this is only constant in the horizontal direction because you can't look at the force of gravity. In real life, the velocity might not stay constant during the entire experiment because due to the friction on the ground and then maybe how full the ball is of air. Many different human errors come into contact with that, as so did in mine when I did the tracker. Different human errors occurred. But in a perfect scenario, the momentum and the velocity would stay constant. This lab shows that in a collision, the momentum and the energy principle is satisfied, stating that the momentum final is equal to the momentum initial. And we can also use that knowing that the change in energy is equal to 0, as is the work and change in kinetic energy, as because the F net equals 0 and the velocity is constant. Thank you.